If a circular loop of wire has a diameter, so the first thing I did was I said, okay, the radius is 0.05 meters because I think I'm going to be using the radius for any of my calculations. It's removed from a magnetic field in 0.2 seconds. What's the averaged induced EMF? So this is a circular loop of wire. I'm going to use Faraday's law, which says the EMF is negative N, change in flux over change in time. Brandon, what's the very first word of this question? One letter. You know what N is then? 1. Is that okay? Uh, change in flux, I usually do this separately. So what's change in anything? It's going to be the final flux minus the initial flux. It says it's removed, so I think I can safely say that the final flux is 0. Remember, flux is the number of magnetic field lines passing through a given area. So I'm going to get negative B times A, and I think what's changing is the magnetic field, not the area, although you could be even changing both. It's going to be negative 0.5 times pi 0.05 squared times pi r squared. I'm going to get a change in flux of, I have no idea, negative 0.5, that's a pretty strong magnetic field, times pi times 0.05 squared. Negative 0.0039, and I'll use my answer button. That's going to go walking over to here. So the EMF is going to be negative. I'll put the 1 there. If you didn't bother writing it, Hannah, that's fine. The change in flux, negative 0.0039 dot, dot, dot. And the time is 0.2. This is not going to be a very big voltage. Negative 1 times answer button divided by 0.2. You get 0.0196 volts. Is that right? No? Yeah? I clearly need to make these numbers a little different to make it more interesting, but 0.0196. I would also have to accept, I would also take negative 0.0196 because you could have decided to let the direction of this magnetic field be negative because magnetic field is a vector. So I would take either, Nicole, plus or minus. If you got that 4 out of 4, otherwise, I would probably go something like this. I would give you 1 mark if I saw that you'd recognize that we're using Faraday's law. I would give you, I think, 1 mark if I saw flux written out, 1 mark for finding flux, and 1 mark for the answer. Induced EMF in a wire. So Victor, for a wire, we do an induced EMF of BLV. It's going to be 0.4 times L times 25. I did a double check. Victor, what word did I just underline? Everything does have to be at right angles. Hey, they said it was at right angles. That's great. So it's going to be 0.4 times 0.5 times 25. And, oh, that's better. 5 volts. I'll add the 0.0 just to go to 2 sig figs, as is my wont. I would probably go something like this. 1 mark for identifying the correct approach, half mark for the numbers, half mark for the answers. Ooh, now they want the current flowing through the wire. You know what? I think this is going to be a review. I think it's going to be I equals V over R. It's Ohm's law. And it looks like the voltage is 5. The resistance is 6. So what is 5 divided by 6? Is that 0.833 repeating? Yeah? Amps. Again, probably 1 mark for identifying Ohm's law, half mark for that, half mark for that. If you got answer A wrong, but you did your answer from A divided by 6, I would give you full marks for part B. Ooh, 5 marks This one is more challenging. We have a change in direction. I chose to let the final be negative and the initial be positive. You could also do the other way around. So this answer, I would have to accept either a positive or a negative answer because my choice, Arian, of positive or negative is completely arbitrary. Once the average induced EMF in the coil, again, that's going to be Faraday's law because it's a coil. It's going to be negative N, change in flux over change in time. This time, I don't think N is 1. N, 750. The change in flux is going to be the final flux minus the initial flux. Change in anything, Taya, is always final minus initial. It's going to be B final A minus B initial A. B final is negative 0.45. What's A? Oh, this is nice. They gave me the area. That's a bonus. They calculated it for me. 0.45 minus initial field is 0.75 times 0.45. By the way, is there an A in the first term, Eric? Is there an A in the second term, Eric? Is there an A in everything? Some textbooks will write it as A delta B as your change in flux, but you could also be changing the area. So I always write it as just I always start with the change in flux, and then I derive what's changing, the magnetic field, the area, or both. Let's crunch that, Mr. Dueck. It's going to be negative 0.45 times 0.45, that's interesting, minus 0.75 times 0.45. I get a change in flux of negative 0.5625. What did I say it was? Negative 0.5625. Should I round that off? No. Am I wrong? I forgot a 4. I am wrong. Oh, thank you. Candy for you, Nicole. How about negative 0.54? Is that better, Nicole? I've met with your approval. Finally. By the way, what were the units for magnetic flux? Webers, yeah. I'll put the units there just to jog your memory. The units for all flux is lines, because there's also electric field flux. There's anything that has a field that emits radiation has flux. It's lines, but specifically magnetic flux is Webers. And now I'm going to walk over to here. It's going to be negative 750, negative 0.54 divided by how much time elapsed here? 0.25 seconds. This is going to be a big voltage. You ready? Wow, did you get 1,620 volts? If you got that, 5 out of 5. Otherwise, I would probably go something like this. Again, I think, Kate, 1 mark just for recognizing it's Faraday's law. I would give you 1 mark if I saw that. I would probably give you 1 mark for that. You know what? Not that many marks, Mr. Dueck. I think I'd probably give you a half mark for each of those. Really, what I would be looking for is I would give you 1 mark if I saw that you would let one way be positive and one way be, yeah, okay. What is that at right now? 1, 2, 3. I'd probably give you 1 mark for the flux and 1 mark for that. Is that right? Sure, that might work. Oh, I would have to accept positive or negative because, Dean, you might have chosen to let final be positive and initial be negative. I have to accept that. There's nothing that says up. It has to be positive. You were crunching on a calculator. Did you get a different answer? You checking something? I like that. Ooh, current. I'm getting a little deja vu here. I think current is going to be V over R. Now, by the way, why do I keep saying average current and average voltage? Remember, because this is spinning, you're actually going to get a voltage that looks like a sinusoidal wave, and you'll be getting a current that goes up and down, up and down, up and down as well. which has some challenges but some advantages. We'll talk about some of the advantages tomorrow. But meanwhile, it's going to be 1620, positive or negative, divided by 100. Now, what if you get a negative current? Taya, I would accept that. Really, I haven't told you what direction, clockwise or counterclockwise, the current is flowing. Although I could figure it out. If we were looking from the top, you know what? It's really tough to tell because I can't tell which way this loop is opening. It's a 3D image. When I stare at it, it flips back and forth in my brain. So I'm going to leave that for a second. I can do this in my head. I think 1.62? No, 16.2, right? Amps. 1.62 Dueck. Geez, where'd that come from? Ooh, now we have, never mind, not Lenz's law yet. What's the speed of the loop? Oh, Brendan and Arian, we had to add something to the quiz. If you look at number 4, please, can you, where the, where the resistance is, can you make it 0.5 ohms? I forgot to include that, and that's on me. Although we have a loop of wire, I think the EMF is being initiated by this. Also, it wants a speed. Ella, there's only one EMF equation that has a V in it. I'm going to use that, and really I'm targeting on that single that single piece of wire, Victor, that's perpendicular to the magnetic field and the velocity. These two, the top one and the bottom one, are parallel to the velocity. You're not going to induce an EMF. And this section of wire where the resistor isn't even in the magnetic field. I'm going to get the V by itself. V is going to be E divided by BL. The EMF is 0.75. The magnetic field is 0.25. And the length of wire is 0.42. And I get a speed of, is it 7.14 and change? People nodding? 7.14 meters per second. 1 for that, I think. 1 mark for getting the V by itself, and 1 mark for the answer. What's the current through the resistor? Hey, I'm detecting a bit of a theme here, Mr. Dueck. V over R, it's going to be 0.75. They told me that, divided by 0.5. I should be able to do that in my head. Is it 1.5 amps? Or not? 1.5? Thank you, Kyle. Ooh, what direction does the current flow? You could do this in 2 ways. You could use Lenz's law, but the right-hand rule still works. If we look at our token proton sitting right there, what direction is that proton moving? It's being pulled to the right by whatever's pulling this. So thumb to the right, magnetic field into the page. I think the current is flowing this way, yes? From B to A, am I right? People nodding? 1 mark. Can you give yourself a clear score out of 21, please? Pause.